welcome back. I'm Lisa Blackburn, and this is my YouTube channel that we talk about everything I want to, science and math. And today we're talking about nuclear chemistry in physical science class. So this is it, nuclear changes. And you can see that there's not a whole lot to this. That it's a lot, like I didn't even type it, I just hand wrote it. Let me look at this one more time. Make that a little bit thicker. I think that looks good. Okay, so nuclear changes. So you can see from here that we're going to be learning some Greek letters. That's going to make you feel smart. Okay, so we've already learned a little bit about when there's too many neutrons, it is unstable. So what it gives off is called radioactive decay. So right with this, I think I write a little neater. Radioactive decay. Oh, it's kind of messy. See? That says decay. Radioactive decay. So let me read it to you. The disintegration of an unstable atomic nucleus, because it's too fat, too many neutrons, into one or more different nuclei. So we have little Greek letters of particles that are given off. So imagine you've got a giant, some uranium. Say we got uranium in here, and it's unstable. You saw that when you made it in the PhET lab. Well, it's going to start falling apart. And when it does, it's going to give stuff off, and that is nuclear radiation. So we're going to talk about different things with that, but you can just sort of imagine. So what it gives off is called nuclear radiation. Nuclear radiation is these are the particles that are given off from a nucleus during radioactive decay. I can write better this time. I didn't do much better. Okay, so there are different types of radiation, and some of them you've probably heard of. Anybody know what kind of radiation turns Bruce Banner into the Hulk? Gamma, and that's one of the ones we're going to talk about. There's another one called alpha and one called beta, and we're going to talk about this. And we're going to talk about alpha first. Alpha. That's kind of messy. Alpha particle. Now it turns out, imagine a helium is so big and falling apart. A uranium is so big and falling apart that one of the things that can fall out of it is a whole nother atom. And it turns out that that's true. Helium can come out of a radioactive element when it's falling apart. So this, you know already, is the symbol for helium, right? You learned that in the PhET lab. So that symbol is one of the symbols for alpha decay, but sometimes instead of doing He for helium, they'll do this little fish. That fish is the Greek letter alpha. So sometimes it's like 4/2, the mass of helium, the atomic number of helium, with a little fish. That's the Greek letter alpha, and that's right there. That's one of the kinds of decay that's coming out. So don't you feel smart learning a little Greek letter? That's why we have Little Caesar's pizza guy there. He's Greek, eating some pizza. Okay, so this is really a helium atom. Boy, I'm writing messier today. That says helium, believe it or not. So it has a charge. It's an ion, and it has a positive charge. So it's a cation. And it's big, sorta, as big as an atom can be, but it's big compared to some of this other radiation we're going to talk about. And it's easy to stop. It's easy to stop. Paper will stop it. So, like another kind of radiation you're used to is when you go to the dentist and get your teeth x-rayed, they put a big heavy lead thing on you, don't they? They don't put a paper gown on you. So this has a whole lot more energy than what you get at the dentist. Less energy, yes. Yes, you can. All right. It ionizes, and we know that because it's got a plus charge. Remember, ions are positive. And it changes the atomic mass and the atomic number. So the word, there is a abbreviation for change in science, and it is a triangle. That triangle is the Greek letter delta. So this is accepted for change in science and math. So in science and math class, you never have to write change or difference again. You can always put a triangle, and math and science teachers and mathematicians and scientists know what you mean. So now you've learned two Greek letters, alpha, the little fish, and delta, the triangle. Feeling smart, aren't we? We're talking about bombs and nuclear radiation, and we've already learned two Greek letters. Okay? Yes, changes, and it's a triangle, which means change. When you have alpha radiation, it changes the atomic number and the atomic mass of whatever gave off the alpha particle, whatever had that kind of radiation. Okay, now we've already talked about Hulk. What makes a Hulk? What kind of rays? Gamma. So our next one is gamma. So you had some prior knowledge, some scaffolding. Know about Hulk. The symbol for gamma is this. It looks like the symbol for Aries in astrology a little bit. It looks like a Y that has melted, but that's the symbol. What do y'all think it looks like? Kind of like horns on a stick, but that's it. And it has no mass, and it has no atomic number, so the numbers next to it are 0, 0. Okay? It's a form of light, a form of electromagnetic radiation, and you already know about Roy G. Biv, right? Roy G. Biv is a colorful man. Do y'all know that song from They Might Be Giants? I'll play it for you if y'all remind me. So y'all know about visible. Y'all know about the rainbow. But there's light, electromagnetic radiation on both sides of that. And how I remember it is Ronald McDonald is very ugly, extra gross. Ronald is radio waves. You've heard of those, right? M is microwaves, what cooks your food, what makes your cell phone work. I is infrared heat. V is visible, that's Roy G. Biv. U is ultraviolet, it gives you a tan and gives you skin cancer. X is X-rays, that's what you wear, why you wear the lead at the dentist office. And G is gamma rays. So that G in Ronald McDonald's Very Ugly Extra Gross is gamma rays. So it's really part of that, and it is a form of electromagnetic energy. Now I told you that delta is the accepted abbreviation for the word change. Well, the symbol for energy is a capital E. And probably from now on, I will always write a capital E and not bother writing energy. Okay, so everybody get that in your head. So what it is packets of energy, see, look at me using that big E, called photons. Have you ever heard of photons before? They're little packets of energy in light, photons, okay? This has high energy, and it's hard to stop, much harder than alpha. It takes lead to stop it, and when something undergoes gamma radiation, it changes the energy. I'm using the triangle for change now. Yes, Jalen? Photons. The packets of energy are called photons. Photons. If you've ever learned about light, you learned that light comes in packets of energy called photons. So there are other things given off. One thing that's given off, mine got cut off, I don't know if yours did. Other things, one of it is called positrons, and they're like positive electrons. And you probably don't have to know much about these, but just to let you know, when you get to physics class, you might learn some more. Yes, Jalen?
I'm sorry, what's next to energy?
What?
What's next to energy?
Right there?
Right.
That?
Yeah.
Photons. Packets of energy called photons. They have high energy and they're hard to stop. It takes lead, and it does change the energy of what's being given off. Okay? All right, our next kind, if we got alpha, this one's called beta. Another Greek letter. Its symbol, what it is it's actually an electron. So one of the things that something that has got radioactive decay can give off is electrons. It's symbolized with a little e with a -1 to show that it has no protons. It's -1 electrons with no mass. But sometimes instead of the E for electron, they'll do a Greek letter beta, which looks like a capital B, where the bottom doesn't quite touch and it's got a tail. So now you've learned another Greek letter. We've got alpha, beta, gamma, and delta. We're just zipping along our Greek letters, aren't we? Okay, so this has what charge does an electron have? Negative, so it's a negative charge. It is small. We already knew that, didn't we? The electrons are small. It can be stopped by 3 millimeters of aluminum. So this one's not as dangerous as gamma, but it's more dangerous than alpha. Paper can stop alpha. It takes aluminum foil, the thick kind, maybe a few sheets of it, to stop beta particles. It ionizes. It has a charge. We already knew that. And it changes, it's my triangle, it changes the atomic number. Yes, ma'am?
What is the one above
3 millimeters, 3 mm. 3 millimeters of aluminum can stop it. Now there's another one called neutron emission. And the symbol for it is the same thing as the symbol for a neutron. It's 1/0 lowercase n. Because neutrons have a mass of 1, they have no protons, they have no number, and it's lowercase n because it's a neutron, not nitrogen. It has no charge. We already know that, right? No charge, and it's stopped by lead. So it's pretty high energy. Now, there's one last little thing I want to tell you about this. This is the symbol for caution radiation. And over here is our secret. It says a secret. Can anybody read what this is on your paper? Can you figure out what I'm saying here? That's the symbol for a neutron. And then it says it equals a proton plus an electron. If you take a neutron and hit it hard enough to crack it and break it, it is made out of a proton and electron shoved together. That's shocking, isn't it? And makes sense because the positive and the negative counteract each other and make it neutral. How do we feel about that? Brian, are you awake? You with me? Okay, let's go to page 2. We're a quarter of the way through already. Now, this has to do back with our essential question, which was, how is the law of conservation applied to nuclear reactions? And it is you can't create matter or energy. What you put in is what you get out. So this is a math equation we're going to learn. And there's 2 kinds of nuclear reactions we're going to learn about, alpha and beta. And we're going to talk about beta first. So this is like a math equation, and the arrow is like the equal sign. And so this is saying carbon-14, that is a radioactive form of carbon. It's got too many neutrons, it's falling apart. Can have can have decay. It can give off radiation. And when it does, it gives off a beta particle and something else. This is an equals, and what is on both sides of the equals must be equaled. So mathematically, it must work. What minus 1 is 6? What minus 1 is 6? 7. So right here, our right is 7. What element on the periodic table is number 7? Yes, nitrogen. Y'all are doing awesome. Now we have to do the top numbers. What plus 0 is 14? 14. This is not bad math, is it? You just balanced a nuclear equation. Hooray! That sounds awfully fancy, doesn't it, what you just did? Okay, now let's do an alpha one. What plus 2 is 88? 86. So right here, 86. What element on the periodic table, hint, it's a noble gas, is number 86? Rn, radon. So we can fill that in. Now we got to do the top math. What plus 4 is 226? Yes, 222. Do you think you're going to be able to do this on the test? We're going to practice it. We're going to do some worksheets, but it's not hard, is it? Let's do another one. What plus 2 is 89? 87. What element on the periodic table is 87? It's one more than 86. FR, francium, named after the country Germany. No, France. Okay, let's do the top one. What plus 4 is 217? 213, right? Ta-da! That's not hard, is it? Later on, we'll balance chemical equations, and they're a little harder, but not much. So that is called isotopic notation, isotope notation. So you use isotope notation. Isotope notation. All right, can I scroll up? Does everybody have that? Nope. This little balance is showing that nature likes balance. It has to be balanced on both sides of the equal, and that balance is reflected in the law of conservation. What you put in is what you get out. Yes, Jalen?
What's next to notation in the website?
Isotope. That's called isotope notation. You learned it in your FIT lab, where you write the number of protons on the bottom and the mass on top. Yep, that is called isotope notation. Okay. Now can I scroll on to half-life? So that's our first kind of problem. Here's our second kind of problem. Okay. So if I imagine here I've got my beaker of uranium again, and it's fallen apart. And eventually a bunch of it will have fallen apart and it's become something else. Well, the time it takes for half of it to fall apart has the very creative name of half-life. And it's a time period. It's how long, if you've got a sample that's 100% radioactive substance, how long does it take half of it to fall apart? You still with me, Peyton? Peyton, wake up. You gotta learn how to do this math. So half-life, in each time period, it takes half of it to decay. This is used for dating, figuring out how old a bone is and stuff like that. We'll later talk about this. Got a few problems, but we're not going to learn about the problems. We're just going to learn about how it works right now. Okay, so it has a classic graph, and we're going to be making one of these in lab tomorrow. We won't be using real radioisotopes. We will be using M&Ms, okay, I think, or Skittles. I'll have to decide and figure out which one we're using. All right, so say you start off with a certain amount of chemical, and you've got 100% of it. Well, its half-life time goes down, and say for this one, its half-life is 10 years. So after 10 years, half of it is gone away, and you've only got half of it now. When you wait 10 more years, half of what you have at this point has gone away, and you're down to a quarter. Does that make sense? Now you go 10 more years and half of what you had has gone away, and now you're down to an eighth. 10 more years and you've got half of that left, and you've got a 16th. So this is the classic half-life graph shape. Now theoretically you'd never have none, but in reality you do. And let me explain to you why. If I walk halfway to the door, and then again, and again, and again, I'll never reach the door because I'll always be halfway away. Does that make sense? But in reality, that is an infinity. It's an asymptote. But in reality, real infinities don't exist. They only exist in math class. And I don't completely understand it, but I was reading about it in a math philosophy book. The reason why we know actual infinities don't exist is because there's now. I don't understand it. But according to the math philosophy, that we know there's not actual infinities, because if there was an infinity somewhere between the past and now, we would never reach now. And also with this, it really won't go for infinity. Eventually you're down to one atom and it will decay and they'll all be gone. You can't take half of an atom. Does that make sense to you? So it'll eventually hit it. Now, why are atoms radioactive? Why do they fall apart? Why does having too many or too few neutrons bother them? The reason why is this idea: likes repel. Things that opposites attract, likes repel. You've heard that before. You did it with magnets, right? You took two magnets that were the same and you tried to shove them together, and when they get close, they go and go off of each other, right? No matter how much you push, it's because they were alike. You turn one of those magnets over and they're opposites and they'll attract. They'll stick together. But likes repel. In the atom, everything in the nucleus is positive and it's repelling. So that's one of the reasons. So how does a nucleus stay together then? It is something called the strong force. It's very strong and it acts over a short distance. And it's one of the fundamental forces of nature. And there's a lot not known about it. So if you want to grow up and discover something great, you can figure out the strong force. Now, why are they unstable? It's either too many or too few neutrons. And then another thing that makes them radioactive, if they have protons that are more than 83. So everybody look at the periodic table. See bismuth, number 83? Everything over bismuth, polonium, radon, all of those, they're all radioactive. They're too big. So everything with protons greater, remember greater than, less than signs? And okay, when I was little, we learned it as an alligator or a baby bird. But now I've decided it's Pac-Man. Pac-Man's way easier to draw. So Pac-Man, if the protons are more than 83, then it is going to be radioactive. Also, when one of these things decay, they're more stable. And so a lot of things in nature always go to what's more stable instead of what's less stable. Okay, how do we feel about page 2 of the notes? We're halfway there. Are we doing good? Haven't lost anybody yet? Good. Let's go on to page 3. Nuclear changes. So we're going to talk about bombs and stuff. Okay, so let me tell you, first of all, I'm going to help you remember something, okay? So everybody make one of your hands a fish, make it swim through the water, and the other one is a knife. So your fish is swimming along, and you're going to cut it in half. Poor fish. But nuclear fission is splitting the atom. Do you see my fish on the wall back there, the green one? That's why he's there, is to remind you that fission is chopping it in half. So everybody, when you see that fish, think, chop it in half. Fission is splitting the atom. So let's talk about a little bit about the story of them splitting the atom. So early scientists like Marie Curie and Henri Becquerel were learning about nuclear things. And then it was Germany in 1939, as someone bad was coming to power. Who was coming to power in Germany in the late 30s? Hitler. Hitler was. Okay, so there were some scientists. There was a team of scientists working on this. It was Hans, Strassmann, and Meitner. And they were doing these experiments, they knew uranium was radioactive, and then hit it with stuff and see what happened. Okay, so they had a problem, and it was Hitler. So this is one part of science where religion, politics, and science kind of come together. And especially because a lot of this was developed in this time period. So they were working on this, and the problem was Hahn and Strassmann were okay. They were Aryan Germans, but Meitner was Jewish, and she was a lady, and so they knew that they had to get her out. So Otto Hahn and Fritz Strassmann, they sold their jewelry, they took all their money out of their bank account, and they paid money to get Lisa Meitner out of there to nice, neutral Switzerland where she was safe. They kept doing the experiments, and they would send her the results. Now, she was Jewish by heritage, but not by faith. And this confuses some of my kids. She was Christian. So even though her ancestors had been Jewish, going all the way back to Abraham, her faith was Christian. So she was celebrating Christmas in Switzerland. Everybody's got the story so far. Do you think Hitler cared that she was Christian faith? No. He killed Jews. If they had no faith, he didn't care. He killed them all. Okay, so she is celebrating Christmas with her nephew in Switzerland, and they got a weird thing happen in their lab, and they sent her the documents, and she understood what had happened. Instead, they were thinking when they shot the uranium with some neutrons that they might get, something slightly bigger than uranium, or maybe something slightly smaller. They might get number 90 or 91 or maybe 93 or 94. Instead, they got 56 and 36. Look over there at bromine and krypton. And they said this to her, and we were like, we have no idea. Did we get contamination? What happened to the uranium? And why do we suddenly have bromine and krypton? And Lisa figured it out. She said, you split the atom. The neutrons made it cut in half. And it did. Plus, it gave off more neutrons and energy. So she figured it out. They published it without her name on it. They couldn't have a Jew's name on this paper. It wouldn't have got published. So they were like sort of hailed as heroes of figuring out this new science. Well, meanwhile, there's this guy. Who do you think that is? Einstein. And he's come up with a famous theory. E equals MC squared. Look at all you being so smart already knowing this. Okay? So he had figured this out, and because of that, they realized that this formula could be used as a bomb. It was going to give off a lot of energy. So one of the things it gives off is neutrons. And then the other one is lots of energy. So at this time, Hitler is, it scares people. And we're going into the war, and they realized they could make a bomb out of this. Now, that's pretty shocking. Hitler went to war. Usually when a country attacks, they attack one other country, like Russia has attacked Ukraine. But Hitler went to war with the world, and it was close. That's pretty shocking, isn't it? Like, we weren't sure that we were going to win even. So they decided that they were going to use this information and make a bomb. And it was called the Manhattan Project. Have you ever heard of it? They made two bombs. One was called Fat Man and one was called Little Boy. Japan joined Germany, and so did Italy, in fighting the world. And a lot of scientists went to work on the Manhattan Project. Now, one of them who did not was Einstein. There were a lot of scientists in Chicago who didn't go. And the reason why Einstein said he wouldn't work on it is because he, too, was Jewish. He believed in God. He wasn't practicing. He didn't go to synagogue every week. But he was still Jewish by heritage, and he did believe in God, but he just wasn't practicing the religion. You follow all this? It's a little crazy, but that's what was going on. And he said he would not work on the bomb because of this. He said that historically Jews had been persecuted. Pharaoh tried to kill them. The Babylonians tried to kill them. Rome tried to kill them. Now Hitler is trying to kill them. And he said that if they made this bomb, one day somebody would try to use it on the Jews, and he was not going to be part of anything that would be used against his people. So he said no. And there were a lot of other scientists from Chicago who said no and who protested it because they thought it was too destructive. But we made it in America, and it's extremely destructive and so much energy. 1 kilogram of matter, everybody imagine 1 handful of matter will give off as much energy as 22 million tons of TNT. Can you imagine how big this bomb is? That's why a nuclear bomb is a big deal. So eventually they made them. Germany got defeated before they finished it. They ended up using them on Japan, and we'll talk more about that later. But isn't that just interesting to think about all of this? So this is fission, splitting the atom, nuclear bombs, fission. Now, to have a nuclear bomb, see, that's our fish, you have to have enough stuff. So why it makes a bomb is mass gets changed into energy, okay? And then a chain reaction starts. So if one atom splits, it gives off some neutrons, and those neutrons can hit more atoms and split them. So look back at our equation. Do you see here? You hit this uranium with one neutron, but then 3 more neutrons were made, which could go hit 3 more uraniums, and so on and so on and so on. It's exponentially growing here. And we'll talk more about that later. We're going to do a lab with dominoes where we model chain reactions. So here, one could split, oops, try get writing. Let's make it a little bigger, see if it likes that. Yeah, it likes that. Okay, one here in my drawing splits 2, and so on. And the neutrons can cause more atoms to split. You have to have enough stuff, it's called the critical mass. I like whoever named this stuff. You know, half-life, enough stuff is called the critical mass. It's all pretty easy to remember, okay? And it's used for, what's that? You know what that is? That's the mushroom cloud. It's used for bombs, but it's also used for power. A nuclear power plant uses fission. In bombs, it's uncontrolled. In power plants, it can be controlled. They have something called control rods. How you get electricity from nuclear power is they use the heat it gives off to boil water that makes steam that turns a pinwheel. I used to have a Winnie the Pooh pinwheel I would bring out for this and blow on it. You have to imagine it because it got crushed. Poor Winnie. But it turns a pinwheel that moves magnets near a wire, and it makes electricity. I didn't really leave enough room for my blank. Electricity. So we'll talk more about how electricity is made, but mainly you're just boiling water different ways. Or what you have to do is you have to move a magnet near a wire. That's how you make electricity. Any questions about page 3? Everybody good so far? Jalen, you with me? Mm-hmm. Okay, so we had the fission, now fusion. What makes this hard is they both start with the letter F. So now we're going to learn what fusion is. Okay, everybody, imagine you've got a hydrogen in this hand. Get your hand out. Get a hydrogen in the other hand, and we're going to squish them together into a helium, and that gives off energy and make it shine like the sun. So fusion is hydrogen being squished together into helium, and it shines like the sun. See the sun over the fish? That's why it's there, to remind you that fusion makes the sun shine. Fission is splitting the atom. Are we good with that? You got those two things in your head? Fuse, you're fusing it together. Fission, you're cutting it. Okay? So, for our last page here, where the energy comes from is still equals mc squared. When you squish 2 hydrogens together, it makes helium, but also radiation and energy. Okay? And the order of the radiation is not just visible light, it's all of them. Ronald McDonald is very ugly, extra gross, including those gamma rays, and it actually gives off more stuff too. Okay? But that's what makes the sunshine. Fuse means join together. Now, is this good or bad? Well, let's talk about it. Can I scroll?
No.
No. Whoop. We're going to talk about, is it good or is it bad? Yes, Nick?
What's next to V?
VG. Wait a minute. Ronald McDonald is very, that should be ugly. Not another G. Let's do that one too. All right, those neater. Oops, come back to draw. Very ugly. That's better. Very ugly, extra gross. Okay, now you ready to scroll? You good? Do we have it? So there's our sun shining. Fusion. Up to our last page. E equals mc squared. Same reason why it gives off energy. It's hydrogen plus hydrogen makes helium. That's a fusion reaction. It's going to give off energy, radiation. All of it. Ronald McDonald is very ugly, extra gross, plus more stuff.
I'm good. I'm good.
Okay, now let's scroll. Okay, so the good. The sun. Could we have life on our planet without the sun? So now when your little kid says, Mommy, Daddy, why does the sun shine? You can say, nuclear fusion. Okay, also stars. I think stars are great. They're beautiful. Very nice to have the whole universe out there, not just sun. Also, it's useful in smoke detectors. They use radiation in smoke detectors. That's good. Not burning up. Another one is they can detect disease. They can use radiation to detect disease. Can detect disease. Also, radiation can be used for therapy to cure cancer. My brother had cancer. He had Hodgkin's lymphoma. And they shot him with radiation, and he got no superpowers. It just made him go bald. Not very interesting, but he doesn't have cancer anymore. They can use it for tracers in your body, or even they'll use it like in industry. It can be used as a disinfectant for food. They'll take potatoes and irradiate them, put radiation on them, and then they don't go bad for a long time. It's used to make power, electricity. We have a power plant in Georgia that makes electricity with nuclear power. I think it's Plant Vogel. So all of that's pretty good, right? Now what's bad about it? It can cause cancer, so that's kind of weird that it can cure cancer, but it also can cause cancer. Isn't that weird? Also, I'm going to say bombs are bad. You know, maybe if you're a military person, you might think bombs are good, killing the bad guys and letting the good guys live. But I'm still putting bombs in the bad category. If you want to write it in the other category, you can feel free. Also, radiation sickness. If you get exposed to radiation, it'll kill you. A couple of the guys who worked on the Manhattan Project got exposed to radiation and died. And what it does is it will cook you like a hot dog in the microwave oven from the inside out. It will cook you. So, you know, that's bad. If you get exposed to radiation and you die, that would be bad. Radon is bad. Radon is a radioactive gas that we have in the dirt here in Georgia in our red clay. It seeps up to houses. It's colorless and odorless, and it'll give you lung cancer when you never smoked. So there are radon detection kits, and before you sell your house, you have to prove that it doesn't have radon in it, because radon's a problem here with our dirt. Not only is it hard to get out of your clothes, but it can give off radon. Another problem is nuclear waste. After you have made nuclear power, what do you do with the leftover stuff? Nobody wants it in their backyard. So that's a problem too. Now, the dream, okay? So fission is what they use for nuclear power. But the dream is if we could ever have power, instead of using fusion, uranium, if we could do fusion instead of fission, that would solve our energy problems. Because if you take hydrogens and put them into helium, helium's safe. We put it in balloons. Probably some of you have even breathed it in to make your voice sound weird, right? So it would be safe energy. You've never heard of doing that? People do that sometimes.
I've done it before.
You've done it before? I'll turn it in for you. I'm excited you got that together, Lori.
Did that say cold fusion?
Cold fusion. So right now, to have fusion, to have a fusion bomb, you have to light it at extreme temperatures with a fission bomb. So, but if you could get fusion where you could have it at room temperature or cold, then we would have no energy problems anymore. Like it'd be like Back to the Future with the car flying with some banana peels kind of thing. So back in the 80s, there was a university in America who claimed that they had got cold fusion. Turns out they had lied about their results. Last week, there was a university who claimed that they were able to get net positive energy fusion, which means they got more energy out than they put in. It was a very big deal, but I'm skeptical. I've been lied to about cold fusion before, and so I'm a little skeptical. We're just going to wait and see if that experiment can be replicated. All right, so that is this chapter. Does that seem easy? Pretty good? Not too hard. We won't have the test until next Thursday, not tomorrow, but Thursday week. Let me turn this off. I always say, oh yeah, science is great. Like, share, subscribe.